Dr. S.S. Wangikar sir, who is head of department of our college, and under the guidance of him, we are going to organize this FDP from 13th June to 18th June 2022. Now, I request to give introduction of our department by Dr. S.S. Wangikar sir. So I request S.S. Wangikar sir to please continue with our department introduction. I hand over chair to Wangikar sir. Hello. Hello.
Sir. Sir is joining. Wait.
Okay, within few minutes. Before that, let me tell you, schedule has been mailed to everybody, every participant, and we are going to stick with the schedule. So, and also we are going to have hands-on practice for this COMSOL software, which is very useful for the research purpose. Yes, welcome, Wangikar sir. Now I hand over charge to you. Please give some introduction of our department. Thank you, sir.
Okay. Very good morning to all.
Good morning, sir. Good morning.
Okay, so I take privilege to welcome all the participants for this numerical simulation and analysis with COMSOL Multiphysics. Starting from today, 13 June, and it will be up to 18 June. And this workshop FDP is in collaboration with COMSOL. Okay, so before starting, as the Swedish College of Engineering is situated in Pandharpur, the South Kashi, we can call, and the spiritual capital of Maharashtra. So we start every event with the name of Lord Vithala and Mata Rukmini. So Sakala Mangalanidhi Sri Vitthalache Namadi. So we start all the good works and all the things by the name of Sri Lord Vithala. So I welcome you all for this 1 week virtual faculty development program on numerical simulation and analysis with COMSOL Multiphysics in collaboration with COMSOL. So schedule, you all are knowing, still just for your information, the schedule is here. So 13th and 14th sessions will be handled by the experts from the COMSOL, and then on 15th the session is there from Dr. Bhargav and Dr. R.R. Kidde. Then 16th Dr. Hakim and Professor Digvijay ji, and on 17th Mr. Ali and Mr. Kazim, and then 18th practice and validatory functions. So if you have a look towards this, so starting from CFD, heat transfer, then very simple basic engineering problem, then teaching applications, microfluidics, then physics of a droplet, thermal, and then BTMS, battery thermal management system, piezoelectric devices, then chemical reactor. So we have tried to cover maximum variety under this COMSOL. And again, the COMSOL has already declared that they will provide you a 14-day license copy so that you can practice with this. So on behalf of Department of Mechanical Engineering, Swedish College of Engineering, Pandharpur, I welcome all the participants from all over India who have joined this 1 week virtual FDP. I welcome them, and now I will take privilege to introduce Sweri, and then related to Department of Mechanical Engineering. Okay, so Sweri had started in 1998 with student capacity of 160, and now you can see in 2022 The student capacity, including all, is more than 4,000. So a building infrastructure, etc., all the things are there in SWERI. We are having degree engineering, then diploma engineering, then Master of Business Administration, MBA, and then D Pharmacy, B Pharmacy, M Pharmacy. 3 boys hostel, 3 girls hostel. Okay, so highlights of SWERI I will share. So very first, we are having excellent academic results, always top in our Punyasloka Ahilyadevi Holkar Solapur University, Solapur, and maximum rankers in the university from our SWERI. Then we are having excellent accreditations. I will speak later. Then we are having excellent infrastructure, campus of total 27 acres with all the facilities and state-of-art laboratories available for academics as well as maximum for research also. Then excellent research and development. Research fund around 9 crores has been received, and again recently 5 crores sanctioned. So this figure will now become 14 crores fund. And then we are having excellent placement. So these are the highlights of SWERI College of Engineering, Pandharpur. And let us have a look towards accreditations approved by AICT affiliated to Punyasloka Ahilyadevi Holkar Solapur University, Solapur. All the eligible programs accredited by NBA, 2 times accredited and 1 time extended. So 3 times we are accredited by NBA, then NAC accreditation, ISO, then 4-star rating for Institution Innovation Council, band excellent by ARIA, and then accreditation accredited by Institution of Engineers and accredited by TCS. We are having UG programs, mechanical engineering, computer science and engineering, electronics and telecommunication engineering, civil engineering and electrical engineering with intake of 540. We are having PG programs, MBA, ME mechanical, ME electronics, civil, computer science, and we are recognized as the PhD research center with our affiliated university for mechanical, electronics and telecommunication engineering and civil engineering. So this is detailed about college. Now I will take privilege to have some highlight toward department, and I will give more focus as far as the research is concerned. Academics and placement, we are at good or excellent stage. So I will focus somewhat highlights as far as the research in the Department of Mechanical Engineering. So Department of Mechanical Engineering solely received near about 1 crore grant, and again 3 crore grant in sharing with the other departments and with the institute. So approximately 4 crore total grant is department having, and through this advanced manufacturing lab, vibration analysis lab, chain testing lab, and metallurgy lab, these are the different labs developed by departments. And as an outcome of this research ecosystem, in last 5 years, 287 publications, peer-reviewed publications, then 7 awards for the faculty members, then 6 patents published. Out of that, 1 is from student side, and different products developed by students. So these are the some of the research grants from RGSTC, AICT, BRNS, then Rajiv Gandhi Science and Technology Commission, DST, etc. So I want to give here highlight on the advanced manufacturing lab. This is the research center. So there we are having the facility of laser engraving and laser cutting machine. Then we are having the micro milling and 3D printing machine. Then we are having the rheometer and rapid eye vision 5 microscope. So whatever micro components we are manufacturing, we will be able to check the dimensions and further characterization with the help of this rapid eye vision 5 micrometer. Then chemical weight bench in order to have some controlled atmosphere and some reactions and some further activities as far as this microfluidics is concerned. The chemical weight bench is used. Then 3D PCM, this is the 27 lakhs proposal sanctioned by BRNS, and this facility is installed at SWERI, that is 3D photochemical machining, and here photochemical machining. This is 2D photochemical machining. So this is the maximum facilities are related to micro, and as an outcome of this all facilities, here you can see different components fabricated by students by using this and this level of characterization. So a hair is shown, and we can measure the dimension of hair also. Up to 5 micron we can measure, and this characterization can be possible by using that particular machine. So here the straightness and the dimension checking is shown. And as an outcome of this particular laboratory, many students have completed PhD, pursuing PhD, MTech and UG. And this lab is having more than 50 publications as a contribution towards Department of Mechanical Engineering. Then we are having this MODROP project for metallurgy lab, and we are having this indigenous micro hardness tester, then inverted metallurgical microscope, then chemical analyzer tester, and this wear testing machine. So these are the different things which are available in metallurgy lab. Then we are having the CNC and VMC machine center, though we are academic institute, but as the setup is in industry, we are having the similar industrial setup in our institute in workshop. That is, we call it as a production center. So there are CNC machine and vertical milling center is there. As an outcome of the same, we are generating consultancy out of it. Then we are having 12 MOUs, and we are conducting different activities with these MOUs. Very important, we are having the American Society for Heating, Refrigeration and Air Conditioning Engineers, ASHRAE student chapter, and it is also run by Professor Digvijay Rongesar, and under his leadership, we are conducting different activities, and a grant of $3,000 has been sanctioned for one of the projects through ASHRAE student chapter Pandharpur, and through this also in the last week only the Spices AICT Spices grant has been received, 1 lakh grant for this ASHRAE activities only. So this is our dynamic chapter conducting different activities. Then we are having the MESA, and through MESA also we are conducting different activities, national level symposiums, and then aircraft workshop, robo workshop, model exhibitions, co-curricular and extracurricular activities also we are organizing on continuous basis. Then moving to the best practice of the department. So last 2-3 years we have started. We have been taking efforts from many years, but last 3 years, whatever efforts we have taken, we started to give some fruits, and as an outcome of the same, our student publication in last 3 years is about 80, and more than 300 students have involved in this research publication and conference. And again, they are actively taking part and winning the international conference, though are UG, winning the international conference first prize, second prize. This is the one of the good thing that we have started, and our students are actively involved, and we are moving toward the inculcation of research culture among the students. Then these are the different products developed, so to satisfy the need of industry and to satisfy the local needs. So first product, lag bangle machine. As the Pandharpur is the holy place, and there are 4 waris in Marathi. Wari is the Marathi word where pilgrims are visiting. So now in the month of July, approximately 15 lakhs pilgrims are visiting, and remaining 3 waris also. Like that, total you can say 30 to 35 lakhs pilgrims in Wari only. They are visiting to Pandharpur, and one of the famous you can say product is the lag bangle. So there are various operations in production of the lag bangles, and one of the hazardous operation in production of the lag bangles is the preparation of mixture. It is also hazardous, fumes are there, and not safely. So the worker who is operating it get more and more injuries. So in order to solve some up to problem up to full level or some level, so we have solved this problem up to 50 to 60%. We have developed a lag bangle machine. It will mix, and it will give the ready mixture for the production of lag bangle machines. And we have deployed the technology on trial basis to we can say persons from Pandharpur are using this machine, and further we are in the phase of commercialization of the machine. Then this is hydraulic operated tailstock. So we cannot drill directly 50 mm. So as a mechanical engineer, we all are knowing that we are go for pilot drill, and then 5 mm, 10 mm, 15, 20, 30, 40, and 50. So this is the need of top gears, and for their product we have developed hydraulic operated tailstock, and we have also patented for this. With this we can drill directly 50 mm drill in one stroke, and without manual operation, just hydraulic operated. You have to put knob on and off. And then these are some other tools fabricated by our students. And lastly, the onion planting machine. We are doing also many activities for the societal development, and as one part of this, different onions we observe in market. The small size onion will have the low price, and quite bigger size they have good price. So in order to have the uniform size onion, the onion planting or onion boring machine is developed. And again, you can see in the picture, the first trial is also taken, and second trial is in progress. and now we are calculating that what is the yield and how they are getting uniform size. And for this project, DPEX 2020 state level technical symposium, our students have received the first prize. So friends, these are the different activities as far as this mechanical engineering department and student and faculty research is concerned. And in addition to this, COMSOL has a very COMSOL software has a, we can say, lion's share in our department of publication. So many of the faculty members are already working in the area microfluidics, heat sink, then piezoelectric pump, etc. And they have whatever ACI good scopus publications are there, the 50% or more than 50% share can be given to the simulations performed by using this COMSOL Multiphysics 5 software. So a very good software, a user-friendly software, and easy to learn. And again, there are many features so that you can operate. So these are the good things for this software. So with this, once again, I welcome all the participants, and for this 1 week virtual faculty development program on numerical simulation analysis with COMSOL Multiphysics from Department of Mechanical Engineering, Swedish College of Engineering, Pandharpur. I wish you all the best. I wish that you will take maximum out of this workshop, and it will be definitely useful for your further research work. Thank you very much. Over from my side.
Thank you, sir. With this, I would like to thanks to Dr. S. Swangekar, sir, Head of Department Mechanical Engineering, Swedish College of Engineering, Pandharpur. With this, also, I would like to thanks to Dr. Ronge, sir, for allowing us to have such a platform for getting the research, we can say, motivation, and also research environment, and allowing us to arrange such type of programs and FDPs. Also, I'd like to thank all the management of Swedish College of Engineering, Pandharpur, and all the deans and all the faculties who have supported to arrange this FDP with this level. Especially Digvijay Ronge sir, then Kachit sir, and all the team, Kale sir, all this team. I would like to thank even all the faculties from the mechanical engineering department also. So I declare with the permission of Dr. S. Swangekar sir that inauguration of our FDP has over, and we are moving towards the first session of this FDP. So before that, I would like to give some instruction to all the participants. That first instruction is that after some time, I'm going to share one link on our group, WhatsApp group. So it is requested to every participant that you have to download that link, and on that link you have to download the COMSOL software, which will be available on your PC for next 15 days, so that we can have hands-on practice with the COMSOL, and we will be familiar with the COMSOL, so that we come to know that how we can do analysis and all that meshing and all things related to the COMSOL. Okay. So second thing is that it is requested to every participant to join each and every session, and if you have any question or query, you can text or you can directly ask to the speaker or the organizers. So these are the some instructions. I will say more than instruction. These are the requests for each and every participant in this FDP. Now, just I'll check. Martin sir, have you joined?
Yeah, I joined. I'm here.
Yeah. Thank you, sir. Now let me introduce to today's speaker, first speaker, who is going to give us hands-on. Also, he's going to explain the COMSOL multiphysics for CFD, heat transfer, and structural mechanics, which are very, very important areas. You can say CFD, all of us, we know that how vast and big area it is, how emerging area it is, and also how we can use this COMSOL multiphysics for heat transfer and structural mechanics. So we have covered all the areas from the mechanical engineering, that is heat and mass transfer, then design related, because structural mechanics comes under the design, and as well as some part we can use for the manufacturing and all other streams of the mechanical engineering. So let me introduce first Martin sir. Dr. Martin sir is working as an applications engineer who joined COMSOL as a technical cell engineer in 2021. He has get his bachelor's degree in mechanical engineering from SCM's School of Engineering and Technology. He has received his Master in Science and PhD from IIT Madras in Biometric Design. And now currently he is working with the COMSOL, and he is going to give us more details related to the COMSOL multiphysics, how we can utilize it for CFD, heat transfer, and structural mechanics. So I request Martin sir to please, you can share your screen and we can start your session.
I think actually you need to make me a presenter because I'm unable to share my screen.
Yeah, sure. Just a minute, sir. Just a minute.
Yeah.
Parke sir, can you listen me?
Yes, sir.
Will you make Martin sir presenter so that he can share his screen?
Sir, can you check now? Are you able to share the screen? Yes.
Yeah, I think.
Yeah.
I hope that actually you can see my screen also.
Yes, sir. Yes.
So thank you so much for such a warm welcome. So I'm Antis K. Martin. I'm looking after CFD and heat transfer in COMSOL Multiphysics. So today I will introduce you to COMSOL Multiphysics and some of the CFD capabilities and heat transfer as well. So these are the agenda we are going to cover here. So we'll be discussing a brief about COMSOL Multiphysics, then the product suite, which all are the products which are readily available. Then 1 or 2 case studies. Case studies are nothing but user stories, how people have been using COMSOL tool across the academics and industries. Then, of course, the CFD capabilities, heat transfer capabilities, and the keyword multi-physics capabilities, followed by a small demonstration and discussion. Now, we are a Swedish company where we have a bunch of offices in Europe, North America, South America. Right now in India, we are from Bangalore, where I am from application team, where it's a full-fledged office where we have sales team, inside sales team, applications team, marketing team, development team. So as a company, we are focusing more on flexibility and accuracy. Definitely, I will explain what do you mean by flexibility and accuracy going forward. So we are providing ready-made physics interfaces, which will help you to capture the real-life scenario as it is. So as I mentioned, the accuracy, of course, if you want to get the accuracy, you need to have the multi-physics. So let us take the CFD and heat transfer. We know that for every engineering scenario or for every engineering physics, CFD is inevitable, either in the form of air or in the form of other fluids. Along with that, actually, we have general mathematics interfaces. Suppose you are interested in your own user-defined equations. We call it as equation-based modeling. You can put your own equations. You can create the geometry inside in COMSOL, or you can import the same from some other platforms. And as a development tool, we have model builder, application builder, and physics builder. So model builder is nothing but how you are going to model the problem. And after that, you can convert your model file to a COMSOL application. So of course, you will be getting a better idea maybe tomorrow. So my colleagues will come into picture for the same. And to deploy this application, you need to have the COMSOL compiler or COMSOL server. Now let us talk about the COMSOL multiphysics or the word accuracy. So in order to capture the real life scenario as it is, you need to couple different physics. So I'm going to take an example of electric motor. We know that for an electric motor, there will be electric current, magnetic field. So let us assume that it's going to be electromagnetics only. So by using this electromagnetic interfaces or physics, you will be able to understand the behavior of electric motor. But we know that when an electric motor is rotating, there will be heat generation. And it's really important to understand how much heat is getting generated. So you can couple electromagnetics and heat transfer, that too by using a single GUI, you will be able to understand how much heat is getting generated. Similarly, if there is a heat transfer, then it is really important to control that heat. So now the CFD will also come into picture. So again, let me use that word again. It's going to be a single GUI. So you can couple electromagnetics, heat transfer, and fluid to understand how much heat is getting generated and how much velocity or how much fluid is required to carry away that particular heat. Along with that, actually, as I mentioned, suppose if you are interested in your own equation, you can go for equation-based modeling, and you can couple the same with n number of physics from the interface itself. So, and you can convert the same to a COMSOL applications. So these are the products which are readily available in COMSOL, especially in 6.0. So the left side, you can see a green color, which is, blue color, which is actually COMSOL multiphysics base package. I would say the backbone or heart of COMSOL software. With this base package itself, you will be able to address linear structural mechanics problems, laminar flow, single phase flow, linear acoustics, pre-processing, post-processing, all kinds of solvers are there in this base package itself. Now, suppose you are interested or you want to capture the more complicated, or you want to capture the real life scenario as it is. Then we have some ready-made interfaces which will help you to capture all the problems as it is. So I will give details about some of the modules. So we have 4 different physics. Let me start with Electromagnetics module. So we have AC/DC module to understand or for the low frequency electromagnetics applications. RF is actually for high frequency electromagnetics applications. Wave optics is actually for long range wave optics. Then ray optics, plasma, semiconductor. The word itself is self-explanatory. Now coming to the fluid and heat, where I will be focusing more. My colleague, Mr. Prawal, he will be focusing more on the structural and acoustics, maybe in the next session. So let me take one by one. Suppose you are interested in turbulent flows or you are interested in multi-phase flow, then you need to have the CFD module. Suppose you are, fluid is non-Newtonian or you are interested in polymer flow kind of approach, then you can make use of polymer flow module. Microfluidics module is really important. Suppose your surface to volume ratio is comparatively higher. An example is blood flow inside a vein. Now coming to the porous media domain or flow, we have Brinkman and Darcy's approach. Subsurface is actually a dedicated one for underground applications. Pipeflow module is actually for really important in the field of your, suppose if your pipe network, the 3D network is very long. We know that at the end of the day, we are solving the Navier-Stokes equation. But suppose assuming a pipe network of 100 meter or 200 meter, the solving the Navier-Stokes equation is actually computationally very expensive. So you can go for Pipeflow approach to address all these kind of problems. And you can couple the, in Pipeflow, you are converting the 3D pipe to 1D pipe, and you can couple the same with any 3D CFD problems as well. So molecular flow module for actually for some kind of vacuum chamber related applications. All kind of metal processing can be addressed by using metal processing module. Suppose you are interested in radiation also, in the sense along with the conduction and convection, you are interested in radiation or phase change, then you can make use of heat transfer module. Coming to the structural and acoustics, suppose you are interested in nonlinear geometry, then you can go for structural mechanics module. Suppose your material itself is nonlinear, Then you can go for non-linear structural materials module, composite module. Geomechanics module is actually a built-in module for soil and rocks. Fatigue module, then rotodynamics module. So my colleague will be explaining all the modules in detail. Now coming to the chemical side. So along with the electromagnetics, fluid and heat and structure, we have chemical modules as well. So chemical reaction engineering module is for all kind of exothermic and endothermic reaction. Battery, of course, the word itself is self-explanatory. Fuel cell, electrodeposition module, corrosion, and electrochemistry. So electrochemistry is a general purpose module. Suppose if you are not interested in other chemical aspects, then you can make use of the electrochemistry module. So along with that, we have multi-purpose modules also. Suppose you want to go for geometry optimization or topology optimization, then you can make use of optimization module. And we have a new addition called uncertainty quantification module in the latest version. And we have a material library where 10,000 different materials. Suppose if you want to understand the characteristics of a body by characteristic of a feature or something related to a material, then you can make use of material library. Particle tracing is actually really important. Suppose if you want to track trace the path of a bubble or a bacteria, then you can make use of particle tracing module, liquid and gas properties module, in addition to the multi-purpose module category as well. Coming to the interfacing, so we have a live links products for other commercial platforms. So what do you mean by live links? Let me take an example of SolidWorks. So live link for SolidWorks means, suppose if you are importing a geometry from SolidWorks to COMSOL, and if you are doing any modification in COMSOL, automatically it will reflect in SolidWorks and vice versa. So it's a kind of bi-directional coupling between the other commercial platforms and COMSOL. Suppose if you just want to import any geometry, then you can make use of CAD import module as well. So these are the modules which are available in COMSOL, and you can couple any physics or any module with the other module, that too by using a single GUI. So this is the typical graphical user interface of COMSOL. So once you open the software, you will get a window like this. So the left side, you can see a model builder window where, similar to our experimental analysis, first of all, we need to have a problem statement or definition. Then either you need to create the geometry or import the geometry. Then we need to go for the material. We need to assign the material, boundary conditions, and the multiphysics coupling, meshing, and the study, followed by the post-processing part. So in the model builder window, you will be getting all the details in a step-by-step approach. And coming to the settings window, where you can input your values like inlet value, outlet value, or any properties or features. Coming to the graphics window, you will be able to see all the pre-processing, like a meshing or the boundary conditions. All the details will be visible here, and you can go for all the post-processing as well. Information window will give you like a maximum value, minimum value, or how the simulation is progressing, and all other kind of information. So similar to the model builder window, we have a ribbon at the top. So this is just to create the user-friendly atmosphere where the whatever things you are getting from model builder, you will be able to see the same at the ribbon window as well. So this interface is going to be remain the same irrespective of the physics you are going to handle. Now let's start with a user story. So case studies are nothing but user story, how people have been using COMSOL tool across the industries and academic. So I have collected one or two. So we will discuss those in detail, and we will understand how people use COMSOL to address their problems. So let us start with the red hot area right nowadays. So that is thermal management of lithium-ion batteries. So we know that we are getting this information through social medias and other LinkedIn profile where the batteries are getting thermally run away or getting damaged because of the hotspot and other information. So in this particular case, it is done by Fiat Italy, where they have, these are not battery, these are cells which are connected through wires. We know that whenever these are connected to wires, there will be current flow and there will be dangerous hotspots. So it is really important to understand where this hotspot is getting happen. And the major challenge they were facing is actually coupling, heat transfer, and the electrochemistry. That too a bidirectional coupling. But in COMSOL, that too by using a single GUI, they were able to couple heat transfer and electrochemistry. Thereby, they are able to understand where the dangerous hotspots are coming and able to reduce the design time by 70%. As a company, especially from a battery point of view, as a company, it's really important to reduce the design time. So with the help of COMSOL, they were able to reduce the design time by 70%, Thereby, they were able to increase the productivity. So you can here at the right side, you can see results of the numerical study. How beautifully COMSOL captured the experimental results. And they got only a maximum 1 degree difference, which means actually it's coming around 95 plus the accuracy. Now, in some points, actually they were managed to capture the same value as well. Let's go to the modeling in COMSOL multiphysics. So as of now, we discussed about the different modules and how COMSOL is coupling the other physics. Now let us discuss about how modeling is happening in COMSOL. So these are the general equations. Of course, we are dealing with partial differential equation, and these are some of the equations like convection, diffusion equation, DC conductive, electrostatics, acoustics, Navier-Stokes equation. Now, how COMSOL solve this partial differential equation? So of course, let me take an example of heat conduction partial differential equation. In that, you can see a general form of PDE. So by correlating the same, here you can see for the second order term, there is no term, which means EA is going to remain the 0. Similarly, COMSOL will compare the equation with the general form of partial differential equation, and it will read the terms as per the equation from our side. Not only for the inbuilt equation, but also for your equation-based modeling also, COMSOL will account all these features by using the general form PDE approach. And we'll be wondering who will be doing all these kind of things. In the sense during the simulation. Of course, COMSOL will look after all these kind of things for you. We don't need to worry about this, all features. Now, these are some of the advanced multiphysics capabilities like arbitrary multiphysics coupling. Of course, it is the key important criteria. Now we have multi-scale modeling like different model scales. Now model reduction, then DGFEM, then boundary element methods. Let us discuss about the workflow in COMSOL. So as I mentioned, before going to model anything in COMSOL, not only in COMSOL, even in the experimental side also, we need to have a problem statement. After that, we need to create the geometry or import the geometry. Because in COMSOL, you have an option to create the geometry to a large extent. So you don't need to depend on other commercial platforms or other open platforms. We can definitely do the same in COMSOL. Then you need to give the materials. You need to assign the materials. Then you need to go for the boundary conditions or physics setup, then meshing, study, and post-processing part. So this workflow is always going to be remain the same, irrespective of the physics. It could be electromagnetics, it could be structure, CFD or heat transfer, or even from the chemical side. The workflow is always going to be remain irrespective of whether it could be a single physics or multi-physics. Now let us discuss some of the CFD capabilities. Let me repeat that word, some of the, because I won't be able to cover all the features, but I will try to cover as much as information I can. So we have non-isothermal flows, high Mach number where the Mach number is greater than 0.3, reacting flows, fluid structure interaction. Of course, this session won't be complete without fluid structure interaction. Then Pipeflow, which is actually really important if your channel network is very long. Particle tracing. I can give you an example. Suppose I'm standing inside a room, and if I'm a pandemic patient, like COVID patient, and if I'm sneezing, then definitely bacteria will be coming out of my mouth. It's really important to understand how these bacteria are moving inside the room. So for this kind of application, you can make use of particle tracing module to understand how the bacteria are moving or how the bubbles are moving inside the fluid. So you'll be able to understand how the movement of the bacteria can affect, or the movement of the materials can affect, or the particles can affect the other human beings or living beings. And we have mixer module, which coupling CFD, free surface, and agitator. And these are some of the heat transfer capabilities. We have Joule heating, induction heating, microwave heating, laser heating, thermal stress, freeze drying. I know that freeze drying is actually a kind of focused area, but still it's really important because we know that it is really important in the field of pharma and other medical industries, and evaporating cooling. So we will discuss some of the CFD capabilities, some of this in detail. So let us start with the CFD modeling capabilities. So of course, as a CFD tool or a modeling tool, we have single phase flows. Suppose your inertia, viscous force is highly dominating our inertia force. Then you can neglect the inertia term from the Navier-Stokes equation. We call it a Stokes flow. Then we can go for laminar flow. Of course, you can model Newtonian and non-Newtonian fluids like a blood flow. Then you can go for, suppose your flow regime is in turbulent region, then you can go for turbulence flow. In COMSOL, we have nine different turbulence model. So here we can see the turbulence model available in COMSOL. So from here, top to bottom, the computational cost will be higher without compromising the accuracy. Suppose you are interested in capturing the surface characteristics in detail, then you can go for LES approaches. And we have an addition called viscoelastic, and you can model the two-phase viscoelastic flow as well. And these are some of the turbulence model where the academics and industry people will be really interested. So suppose actually you are interested in capturing the surface characteristics like lift or drag. An example is actually an oscillating foil, where you are interested to understand how much lift and drag or thrust is actually coming. Then you can make use of K omega or SST model. So the right side, you can see how beautifully COMSOL captured the experimental results. And you will be able to see around 95 plus percentage of agreement between the numerical and experimental results. Similarly, suppose you are not interested in capturing the surface characteristics. An example is flow through a inside pipe or cooling device, electronic devices. Then you can go for K epsilon models. Of course, there will be some difference between the computational cost and the accuracy. So without compromising the accuracy, by reducing the computational cost, you will be able to model all this kind of problems by using these turbulence models. Again, these are the transport equation turbulence model. We have SA and V2F models. These are comparatively inexpensive and less accurate. So these are viable. So these are robust and computationally inexpensive, but of course, by compromising the same with the accuracy part. Now coming to the inelastic non-Newtonian model. So to capture the non-Newtonian behavior, you can have these models, power law, Carrier. So these models are available in CFD, and you can see a star symbol here. So these star symbol models are available only in polymer flow, which is actually a dedicated feature in polymer. So among the modules, we have dedicated and overlapping features. So as per your requirement only, you will be able to select the modules. So the right side, you can see a blood flow inside a vein, and you can see how COMSOL beautifully captured these stresses over the surface of the bed. As I mentioned, we have viscoelastic models as well. So the star sign indicates that this is available only in polymer flow module. Now coming to the multi-phase flow approach. So we have two different types of approaches. One is separated flow and another one is displace flow. So what do you mean by separated flow? Separated flow means actually, suppose your interface is very large or the interface is comparatively larger than that of the fluid. An example is actually a water inside a bottle or a reverse free surface. So there you can go for separated flow approaches. So we have again level set, phase field and approaches. You can even go for three phase also. Then what do you mean by displace flow approach? Suppose your interface is very small compared to that of the fluid. So like a bubbles, or here you can see so many bubbles where the interface is comparatively small. Then of course you can model the same by using separated flow, but the computational cost will be very high because the mesh density should be comparatively higher for the separated flow. There in this kind of scenario, without compromising the accuracy, you can go for displace flow approach, where we have bubbly flow, which is actually for liquid and gas. Then mixer model approach, which is for liquid and gas and soil and liquid. Then Euler model, which is an industry standard model where you can where the equilibrium assumption is not there, which means actually the relative velocity between the bubble and the fluid won't be zero. Then we have phase transport approach, and these approaches can be used to model this kind of displace flow problems. Now we will discuss more on the multiphysics capabilities. So we have conjugate heat transfer, reaction engineering, particle tracing, and fluid structure interaction. So let us discuss each physics or each multiphysics problem in detail. So first thing is conjugate heat transfer. So let me take an example of a CPU in front of us. We know that inside the CPU, there will be conduction, free convection, forced convection, and you can see a fan there. So let me assume that this particular space is going to be a fan. In COMSOL, we have an explicit boundary condition called fan, where you can model the fan features. The advantage is by using the same, you'll be able to reduce the computational cost to a large extent. So these kind of problems can be addressed by using a single GUI. So which are the physics are coming into picture here, which means CFD is there, heat transfer is there. So you'll be able to couple these two by using a single GUI, and you will be able to address all your problems. So let me take an example from the industry as well. So this is actually a cooling unit of a molding system, where there will be conduction, convection, radiation, phase change, and the convection will be both free convection and forced convection. So in COMSOL, that too by using a single GUI, you will be able to couple all these kind of physics and features to capture the real life scenario. Let us discuss about the reacting flow. We know that actually whenever there is a chemical reaction, there will be heat generation. It's really important to understand how much heat is getting generated. And again, this heat generation can affect the rate of chemical reaction. So there will be a kind of circular dependency. So it is really important to control the heat, and it should be within the limit. So in COMSOL, that too by using a single GUI, you will be able to couple chemical reactions and the heat transfer part to capture all these kind of reacting flows. And of course, you can go for the porous domains and other features also. Now let us discuss about freeze drying. So what do you mean by freeze drying? Freeze drying is the process of removing the excess water content from the final product. So this is actually an example of a skim milk where the extra water content is removing from the, it's a kind of direct sublimation. So to doing this, in this particular case, actually it took around 10 hours to sublimate 85% of the initial ice. So to do the same in COMSOL, here you need to couple heat transfer, CFD, and of course the phase change is there. So and even the porous domain. So you will be able to couple all these physics and features, that too by using a single GUI, and you will be able to get the results within a period of 3-4 minutes. Thereby you'll be able to reduce the design time to a large extent. Now fluid structure interaction. I know that actually this session won't be complete without fluid structure interaction. So here you can see in COMSOL, you can go for two different types of FSI. One is unidirectional and another one is bidirectional. Unidirectional means actually the fluid or the body is deforming the other one. An example is actually a balloon inflation. Bidirectional means an example is oscillating foil or wing, where the fluid path is disturbed by the body, and the fluid body itself is deformed by the fluid force. So in COMSOL, you can model all these kind of problems. So this is actually an example of a fuel tank. We know that especially in this present condition, it will be very difficult to keep our tank always full. So when during the time of acceleration or retardation, there will be sloshing inside the tank. So it is really important to understand how much stress is acting over the walls of the fuel tank. So in COMSOL, that too by using bidirectional or unidirectional approach, you will be able to understand how much stress is acting over the walls as per the liquid inside the tank. Thereby, you'll be able to optimize the fuel tank thickness. Similarly, let us discuss something from the electromagnetic side. So this is actually electromagnetic pump. So what do you mean by electromagnetic pump? So if there is an electric current and a magnetic field which is perpendicular to a electric current, then there will be a third force which will be mutually perpendicular to both magnetic and electric field, which is called Laurent Force. This is really important in the field of nuclear or steel industry, where if you want to move a conductive fluid from one destination to another destination. So in this particular case, as I mentioned, you need to have electric current, you need to have magnetic field, and thereby you'll be able to get the Laurent force. So assuming that it's going to be laminar, so we know that, and the beauty is actually you can even go for the reverse process. Suppose if you want to get the magnetic field, you can move this, or you can force this conductive fluid to move under the electric current to get the magnetic field, which is mutually perpendicular to the other two. So we need to have magnetic field, electric current, and laminar for this particular approach. And here you can see in open boundary condition. In some scenario inside the domain, we won't be able to conclude that it's going to be inlet or outlet. So in those kind of scenario, you can go for open boundary. Open boundary means actually the mass flux is free to move in or move out of the geometry as per the physics setup or the engineering scenario inside the domain. Now coming to the acoustics part. we know that from the acoustics point of view, it's really important to understand how resonance is happening. And this resonance can definitely cause damage to the entire system. So in COMSOL, with the help of a single GUI, you will be able to couple CFD and acoustics to understand how the resonance and other features are happening. Now, coming to the robotic swimmer. So here you can see a body is moving forward with the help of a two wings behind the body. So when the body is oscillating, there will be a reactionary thrust force which will be acting in the opposite direction of propagation. So here you can see how beautifully you can model the same in COMSOL. The body is moving forward. Of course, this is actually a coupling between fluid structure interaction and the rigid body dynamics. Now coming to the peristaltic pump. So this pump is really important in the case of pumping fluids like non-Newtonian fluids like paste or sauce, where or high viscous fluids like sauce or paste. So here you can see the mesh deformation and the corresponding propagation. So in this particular case, the COMSOL couples fluid structure interaction, FSI, and the structural part independently to capture all these kind of scenarios. Now let us discuss some of the heat modeling capabilities. So we have, as I mentioned, you can model all conduction problem, convection problem, and radiation problem. Suppose you are interested only in conduction and convection, then you can make use of the base package itself. Suppose you are interested in the radiation also, then you can go for the heat transfer module. So in the base package itself, as I mentioned, there are so many features where you can put your own equations also, and you can couple the same with any n number of physics. So let us discuss the heat transfer in solid parts. So we have isotropic, anisotropic, linear, and non-linear thermal conductivity. Then of course we have, this is actually an example of a disc brake, where how the temperature is getting distributed over the surface of disc brake. So we have thermal expansion, thermoelastic damping, then electromagnetic heating as well. I will be giving an idea about how to couple the CFD and heat transfer in the hands-on session in the second half. So where you will get an idea how to capture all this kind of real life scenario. Similar to the CFD part, we have laminar and turbulent flow as well. And of course, we have conjugate heat transfer. And as I mentioned, we have a boundary condition called open boundary. And inflow and outflow are similar to inlet and outlet. And of course, we have boundary condition called screen and fan. Suppose if you want to model a fan explicitly, then of course you can do the same. But at the time of machining, the computational cost will be very high. But in COMSOL, we have a specific boundary condition, explicit boundary condition called fan, where you will get all the features and capabilities of the fan explicitly. Screen boundary condition is also available, and you can give the coefficients as well. So let us go to the software part. So I will introduce the software part now. And after that, actually, we'll go for the hands-on in the second session, in the second half. So let me open the COMSOL window. So once you open the COMSOL software, you will get a window like this. In this window, we have two options. One is model wizard and another one is blank model. So if you're selecting blank model, then you need to select the geometry and other features independently. But if you're going for model wizard, then COMSOL will help you to select the boundary conditions and other part. So I will go to the model wizard. Now COMSOL will ask you which dimension you want to select. We have 3D, 2D axisymmetric, 2D, 1D axisymmetric, 1D, and 0D. 0D means actually it's a kind of, suppose you are interested in perfectly mixed system or something like that, where it is actually not independent of the space, then you can go for the 0D. In this particular case, actually, I'm going for a 3D problem. And what I'm planning to do is actually I'm going for a flow inside a cylinder. A simple problem, it's going to be only CFD. So I'm assuming that it's going to be laminar. So here, forget about this recently used. So you'll be able to see interfaces from AC/DC to mathematics. So in the fluid flow, I'm going to open that. So I will be getting features like single phase flow, multi-phase flow, porous media, non-isothermal flows, high Mach number flow. Suppose your Mach number is greater than 0.3, then particle tracing, as I mentioned, suppose if you want to trace the path of a bacteria or a particle, then we have a specific or special interface for fluid structure interaction problems, rarefied flow, then thin film flow, kind of bearings and other things. So in this particular case, I'm going to open the single phase flow, and I know that my flow is going to be laminar. Then I will select laminar. Suppose you are interested in turbulent flows, then you can expand this one and you can select any turbulence model as per your wish. And again, suppose you are not sure about which physics I need to select, then just click over the physics, then COMSOL will give you an information whether this physics is well and good enough for your application. Right now, I know that my problem will be simple with laminar flow. So I will click on Add button. The moment I click on the Add button, I will get the interface here. Now the next step is to study type. So I will go to study type, and in COMSOL we have three different types of studies. One is stationary study, then transient study, and the frequency domain study. Of course, from the CFD point of view, there won't be any frequency domain study. You can go for stationary study or time dependent study. Again, if you are not, if you don't know which study I need to select, then you can read this particular information from COMSOL, so you will be able to get an idea. So let me click on stationary study. Yes. Now I will get a window like this. So here you can see a problem definition and geometry, materials, boundary conditions or physics, meshing, study, and the post-processing part. And we know that there is no multiphysics coupling because we are going to deal only with the laminar. So now my first objective is to create a geometry. So I will go for a cylinder and I will click on the build selected. So I will get a cylinder like this. My radius is 1 meter and height is 1 meter. So I will change the same to 0.5 and I will change the same to 5 meters. So I can create the geometry. So this is going to be my geometry. Now I will go for form union. My geometry part is done. Now next thing is actually I need to select the material. So right click, add materials from library. I will select air as my fluid. Now automatically COMSOL will select the entire domain as air. Now you don't need to worry about the other part because right now we are considering only one fluid. Now coming to the fluid laminar flow. By default, we will be having fluid properties, initial values, wall boundary conditions. And at the laminar flow, you can see we have different options like incompressible flow, weakly compressible flow, and compressible flow. So if you are interested in capturing the gravity effect also, you can check this box. So you will get an additional node called gravity. And these are the by default information and other details. And now go to the fluid properties. So here you can see we are going to assume that it's going to be Newtonian because air is going to be Newtonian. Suppose you are interested in non-Newtonian, you can change the same to non-Newtonian flows where you will be able to change the material as well. Now we are going to use the same initial conditions, and wall I'm going to assume that it's going to be no slip where the tangential velocity is 0. Now let us go with the inlet condition. So right click, inlet. So this is going to be my inlet, and I'm going with the velocity inlet condition and let it be 1 meter per second. Now coming to the outlet part. So this is going to be my outlet. So I'm assuming that it's going to be pressure outlet. So I'm not going to change this. I'm going with the same setup. That's it. My physics setup part is done. And again, I just want to give an additional information. Suppose you found that the flow is not going to be laminar. If it's going to be turbulent, then you will be able to see a turbulence model type. As of now, it is none. You can change the same to RANS, and you will be automatically COMSOL will change the node, and you will be able to select the turbulence model as well. So right now, I'm not going to change. I'm going with the none only. It's going to be laminar only. Now, the next option is in COMSOL, we have two different types of studies. Oh, sorry, meshing type, which is physics control and user control mesh. So physics control means COMSOL will account for the physics and it will do the meshings accordingly. I can give you an example. Suppose in the geometry, we have sharp edges and corners. From the CFD and heat transfer point of view, these are not really important. But from the electromagnetics point of view, these parts are actually really important. So COMSOL will do the meshing as per your physics setup. So once you click on physics control mesh, you will get a 9 options from extremely coarse to extremely fine. So you can vary the mesh types as per your computational capabilities, and you will be able to do the meshing. Suppose if you are not interested in going for physics control mesh, instead of that, if you are going for user control, then you can give the meshings to each domain as per your wish. So yeah, so these are some of the techniques, machine techniques available in COMSOL. At the moment, I'm going for physics control, and I'm going with a coarse mesh where I'm clicking on the build all. Yeah, so now I can see the meshing. So this is the meshing after coarse mesh. Suppose if I want to go for coarser one, then I will click on the coarser and I will click on build all. So it will change. Now, suppose if I want to check the quality of my mesh, then I can right click here and I can go for the plot. So here I can see how the meshing is. So it is always recommended to have a 0.3 plus. So anything less than 0.3 is actually assumed to be a less quality. So it's always recommended to be greater than 0.3. So here you can see it's more towards the green color, which indicates that it's always 0.5 plus or 0.6 plus. Yes. Now we can go for the study. Suppose if you want to see the default solver, then you just click on the right click button and show default solver. So here you can see the default solver and what kind of solvers are used, like a fully coupled. So we have segregated also. So now we'll go for the study. So it will take maybe 1 or 2 minutes. So we'll wait for the results to come. So you can see the convergence plot here. Yes. So we got the default plots like mesh, velocity, and pressure. Suppose I'm just opening the mesh plot, and these are slices. So let me change the same to 1. Yeah. So you'll be able to see how the velocity is changing, and you'll be able to understand how the details are, if you want to capture the details. Now let us go for a streamline plot. So I'll go for streamline, and I will change the same to magnitude control. Let me disable this one. Yeah. So here we can see the streamlines. You can play, I mean, you will be able to do n number of post-processing part, like pressure, velocity, or anything actually you want from here. And suppose if I'm going for arrow. So we will discuss all these things in detail during the hands-on. So I have already shared a geometry with my colleague, so he will share the same with you. So during the hands-on, I will request everyone to follow so that you will be able to understand how the COMSOL modeling and the workflow is happening. So similarly, you can plot anything in COMSOL. I mean, n number of things can be done in COMSOL in the post-processing part. If you are interested in 1D plot or 2D plot, definitely you can go for the same. Suppose if you want to go for a parametric sweep, at the moment I used inlet velocity as 1 meter per second. Suppose if you want to understand how it varies, if I'm increasing the velocity from 1 meter to 5 meter, then you can go for parametric sweep. Similarly, you can do n number of things in COMSOL as per your requirement. So you will be able to get a better idea after this. And as I mentioned, once you create the model file, you can always convert the same to a COMSOL application. So here, the left side corner, you can see a application builder. Click over there. Now you will be getting a window like this. In that, you need to go to new form, global form, and we have several templates for the application. I will go with the basic one. Yes. Now, in the graphics window, I will check for a velocity plot button. I will be going for compute study and done. So it's a simple model. That's the reason actually there is nothing to see, but definitely you can go for your own application models. You will be getting a better idea. Maybe tomorrow my colleagues will be looking into that. So right now you will be seeing a COMSOL application like this, where you can vary the inlet velocity or whatever things you want, and you will be able to capture the, or you will be able to understand how it is varying. So I can tell you an example. Suppose one of your student is asking, so what will happen if I increase the velocity from 1 meter to 2 meter, and how the velocity profile will be, or what will be the outlet condition? If you do that, then you, without using the COMSOL license, the beauty is to run the COMSOL application, you don't need to have the COMSOL license. And you can circulate the same with among your colleagues, students who are not even know how to use the COMSOL software or even any numerical tool. They can simply use this this application like a mobile application, and they'll be able to get the real life scenario, or they'll be able to get the feel of the same thing. Yeah. So now we will go to the question and answer part. So you can definitely ask the question. So I will try to give the answer for the same. So after the session, my colleague will join for the structural part to give a better idea about the how COMSOL is addressing the structural problems and the multiphysics aspects as well. And he will be also showing some demos where you will be able to see how the workflow, in the sense where you will be able to understand there is no difference between the workflow between the CFD and the structural part. So you can ask the questions or you can type the questions. So I will try to answer all the questions from my side. In case if any of the questions are not answered, directly just write a mail to support@comsol.com. So as per the physics interface or physics setup, definitely engineers will come into picture and they will give you the answer for your query.
Good morning, sir.
Yeah, good morning.
Hello, sir. Any physics, any two physics cannot be clubbed together every time. For example, we are using heat transfer in solid and fluid, and another physics we are using the another physics we are using mixture flow. So these two physics cannot be clubbed together.
In the sense, actually, for the heat transfer part, I'm just telling you, we have a dedicated interface called conjugate heat transfer. Means actually it's a heat transfer through conduction and convection fluids. Yes. Mixer part, actually, what kind of applications you are trying to understand? Suppose in the mixer, I'm just assuming that there is a mixer and agitator. If you want to go for the FSI part, like how the agitator is deforming, then you can go for CFD and the structure.
Okay, okay.
I mean, basically, whatever things you want to capture in a realistic way, there you can couple the same in COMSOL. Whatever things actually, yeah.
So suppose in a pipe there is a refrigerant is flowing.
Okay.
And surrounding there is some solid part which is taking the heat, and so we are trying to couple the that heat transfer in solid and fluid with this mixture flow model in the pipe. So these two are not coupling, but these two should be these two physics should be coupled. But when I am trying that, I am trying to couple them, these two are not coupling. But it is a physics which should be coupled.
Definitely. But the thing is, actually, if you can share that model to us through support@comsol.com, I will have a look at the same and I will reply from there.
Okay, sir. Okay, sir.
But try to explain your problem also along with the model file, because we just want to know whether that model is properly modeled or not. Because in some scenario, as I mentioned, we have overlapping and dedicated features. So sometimes you don't need to select some particular physics for your application. So if you can share the model file along with your problem, then we will be able to address the same in a detailed way.
Okay, sir. Okay. And sir, one more question, sir. Suppose we are doing in a pipe, we are flowing a fluid.
Okay.
And we are using the this model heat transfer in solid and fluid, and I want to calculate the Nusselt number or heat transfer coefficient. So sir, how I can calculate, because it is only giving the temperature at the because it is only calculating the temperature. So how I can calculate the heat transfer coefficient or Nusselt number?
Actually, we have a separate block for calculating the Nusselt number. So when you raise a support query, I will share those details also. So you'll be able to address your problem in a detailed way.
Okay, sir. Okay, sir.
So maybe I will be help you. I can help you to let me go to. So here, this is the COMSOL website where when you go down, you can see models and application files.
Yes.
So suppose yeah. So suppose this is the window. This is a landing page. So we have several number of ready-made models available in the application library. So as you mentioned, you are interested in Pipeflow. Suppose if I'm going for just go for the search and you can filter it. So you will be getting so many examples here. So Pipeflow means actually one of our keyword. It's a module. That's the reason we are getting this example from the Pipeflow approach. But you can search the keyword here. As you mentioned, suppose you are interested in conjugate heat transfer. So you will be able to see several examples here from the conjugate point of view. And suppose you want to know more about that particular model file, then you will be able to see a PDF here. Just open that. There you will get all the informations like physics setup, boundary conditions, and how. This is nothing but tutorials. So you'll be able to replicate the same in COMSOL, that too from the geometry level.
Okay, sir.
So this will be useful for you.
Yes, sir. Okay, sir.
So any other questions?
Hello, good morning, sir.
Yeah, good.
Sir, am I audible?
Yeah, audible.
Sir, I am using heat transfer in solid models.
Okay.
Where in that equation there is a term heat transfer QTED, thermoelastic damping.
Okay.
At the time of my simulation, I am unable to understand what it is because nowhere we have to mention that it is, I think QTED is minus alpha into T ds upon dt.
Okay.
What is, where we have to specify that S and how it will work on that model? Can you explain something on that?
So heat transfer in solids, right?
Yes, sir.
Let me open.
Because it's Q plus QTED. Q is the heat source we are using, and the other part is Q thermoelastic damping. I am unable to understand what it is. Yes.
So basically, it is used to include the reverse coupling where the change in stresses act as heat sources. So that's the reason actually that part is coming into picture.
So in that module where I have to insert that stress part, I think it is not showing anywhere in that module. Or just we have to leave that one part QTD because we have to work on a heat source that is capital Q.
So basically, that will be calculated from the study itself. You don't need to explicitly select.
Okay, we don't have to work on that one.
Yeah. So that's the beauty of COMSOL. Actually, these things will happen at the back end where you will be able. You don't need to worry about all this kind of scenario. COMSOL will help you to solve all these kind of problems.
Okay, sir. Okay. Thank you, sir.
Yeah.
Sir, one more question I have.
Yeah, sure.
That I am using that heat transfer in solid, but how we can coupled with partial differential equation for that equation?
Yeah, in the sense actually we have interface called mathematics interface. So you need to go to physics setup. You need to select art physics. So there, forget about the recently used. Below you can see mathematics, right?
Yes, sir.
So in that actually we have different PD interfaces.
Yes.
Yeah, so you can select as per your equation and you can couple the same with the heat transfer in solid part.
It will define that del operator T. It will work on that one of that heat equation.
Yeah, in the sense actually you can select the PDs as per your equation. Right now I'm just assuming that it's going to be a general form of PDE. Suppose you're interested in general form of PDE, you can select that interface and you can put the coefficient as per the equation. Here you can put the source stream, damping and mass coefficient and mass coefficient. Similarly for other physics also, other PDEs also you can do the same.
Okay.
Yeah.
Thank you.
So going forward, actually, my colleague is also here. So he is basically from the structural field. You can, he will be also explaining the things from the structural aspects, and he will be showing a demo as well. So there you can check the workflow and other related information. So maybe if you can, if you want, you can go for a 2-3 minutes break. So after that, actually, we will continue. So Raval, over to you.
Oh, sure, sir. Should we take break?
Yeah, anyway, my colleague is here. He's ready to take the session. If you are interested, definitely you can take a 1 or 2 minutes break. Because it's 11:57 right now.
Yeah, I think it will be.
Okay, sir.
Okay.
Whether he is ready, sir?
Hi, this is Prawal. I think we can take a 5 minutes break. By the time I will set my PPT, right?
Okay, sure. Prawal, sir.
Yeah.
Yeah, sure. We'll take 5-minute break so that you can rejoin with the PPT. So we'll have 5 minutes break.
Yeah.
Thank you. All the participants are requested to have the break of 5 minutes. Okay, we can relax. Just be in meeting. Don't leave meeting. We'll have just 5 minutes. Be relaxed, and we'll again start when the Jain sir is going to join.
Hi, sir.
Hi.
Good morning, sir.
Good afternoon. First of all, let me give some introduction related to the Praval Jain sir. Once again, welcome everybody for this session. It's very good that Marty sir has explained the application of COMSOL multiphysics in various domains like heat transfer and CFD. Now, as we are going to see, that structural part is what we can say mostly used part, and we seek some of the modeling as well as analysis softwares related to structural part. So Praval sir has joined COMSOL as an applications engineer in 2021. He has received his master's degree in mechanical engineering from Birla Institute of Technology and Science, Pillai, where he has worked on structural analysis on non-linear materials. Prior to join this COMSOL, he worked as at a Genu Exhaust Test Limited in product development. He has experience of developing products also and doing the structural analysis. So we hope that Praval sir is going to start his session on especially structural mechanics, how we can do the analysis and how we can go for the simulation. So I request Jain sir to please start your session.
Yeah. Thank you so much, sir, for the brief introduction. Thank you so much for having me here. So let us start with today's session. Today's agenda is I will take you through some very brief introduction to COMSOL multiphysics. I hope Dr. Antis has briefly explained about what is actually the COMSOL multiphysics. Then we'll look at a couple of case studies from structure analysis and its multiphysics coupling with various other physics. We'll see some real world examples where multiphysics can be is actually being used with structure. Then we'll see some modeling capabilities of coming from the structural mechanics. Then we will have a live demonstration on a very brief model. Then we can follow up with any Q&A discussion. I would request anybody, if you have any queries at any point of time, please feel free to ask. I will take up those questions as and when it pops up on my screen, or else anyways, we will be having a question and answers discussion session towards the end of this presentation. So basically, COMSOL multiphysics comprises about from various physics, as you can see on your screen, electromagnetics, structural, acoustics, optimization, fluid. Then we have especially equation-based modeling interface, which makes it very easy to write your own equations. Then we have got live coupling with various other tools. And there's another innovation from COMSOL about the application builder. So basically, it can be very helpful for people like who are not very well versed with the simulations. So let's say for an organization or any commercial industry, we can build an app direct straight through our from our simulation, and in the app we can vary various other input parameters, where various boundary conditions. Then we can evaluate the plots, our post-processing part. So it makes it very easy to distribute this app amongst our colleagues. They can vary these parameters and evaluate the results, which can be helpful in for the development of their products. So these are various other products or modules that have been offered by COMSOL in various other physics domains. We have further addition of multipurpose, where we have got optimization in the field of shape topology, shape optimization, topology optimization. Then we have parameter estimation kind of studies. And our newest edition in this is about the uncertainty quantification module. Then we have got interfacing, as I was mentioning, with various other tools. So this is just a brief overview about this modules that have been offered by COMSOL in the structural analysis. First one is definitely the structural mechanics. Then we have got a submodule, which is a nonlinear structure materials, where you can account for various material non-linearities. You can account for any kind of elastoplastic. Hello. Okay, so where you can account for various kinds of elastoplastic material models. You can account for hyperelasticity, plasticity, viscoelasticity, and various other things. Then we have got a very specialized tool, which is Composite Materials Module. So this makes it very easy to model the composite laminae in COMSOL, and various other post-processing tools, which are very specialized for analyzing these laminates that are very specialized for these kind of materials and laminates, the stacking of all of them. Then we have got Geomechanics Module, which is mostly helpful for the people who belong from the civil department, where special concern has taken care for the soil plasticity, the concrete, and the reinforcement of those bars and all those things, making building dams, and various other applications can be accounted here. Then we have got a fatigue module, which is basically a post-processing tool, so which can be helpful for analyzing the life of a material or a body based upon kind of stresses it has been put up to. It can be any stresses, whether it is a structural stress or thermal stress or any other stresses that have been induced from any other physics, let's say due to the loading through a fluid or due to loading through a magnetic forces. Then we have got a Multibody Dynamics module, which is used for assembly of various other bodies, which have been assembled together with various kind of joints. So it makes it very easy to follow up with those assemblies. We'll talk about all these products in quite some time. Then we have got Rotor Dynamics module, which is specialized for modeling rotating components, the bearings, the rotors, discs, and analyzing Campbell and other and various other plots, the world plots. So this is basically the GUI of COMSOL. I hope everyone of here has got quite a glimpse of how the GUI looks like. So at the left, we have got the model builder, which is basically the modeling workflow also. So let's say the first thing that we define in any of our simulation is building the geometry. Then we go up with defining a material. Then we go follow up with defining the kind of physics that we are working with. And then we if required, we can give a multiphysics coupling with any of the physics that we have defined. Then we go with the meshing of a body. Then we define like what kind of study that we want to perform, whether it is a steady state study or whether it is a transient time dependent study or whether it is a frequency response analysis or is it a modal reduction. And then comes the part of the post-processing where we can analyze various kinds of plots. So just the plots that you see here, which are default plots, which comes in defined as you run the study based on the physics. But anyways, you can add more plots based upon any of the variables that have been defined in the physics. So you can plot exactly any variable on any entity, whether it is a line or surface or the whole volume. So this is basically the graphics window where you can visualize your plots, where you can visualize various tables, and this here is the information window where you can keep track of the progress that our simulation has just now made. Okay, so moving on, I will be showing you some case studies about how our customers have used COMSOL to successfully derive results and have successfully been simulating using COMSOL. And now this brings me to analysis and multiphysics couplings. Okay, the first user story that I have taken here is from the Industrial Technology Research Institute, Taiwan, which is about making predictions in additive manufacturing with simulation apps. So this is basically a thermomechanical simulation, which is used to study an additive manufacturing process. Here, the application was a fuel injector from which is one of the component of rocket engines. And this actually they were 3D manufactured, 3D printing this fuel injector. So actually the issue here that they were facing was that this process it involves highly localized laser heating, which ultimately results in a large thermal gradient in the material. And this gradient that can induce residual thermal stress and deformation in the layers, which basically are being 3D printed here. And this residual deformation, if it becomes very excessive, it can cause the re-equator component of the machine to jam, which basically terminates the whole manufacturing process. And if this manufacturing process jams, it takes a lot of time to again restart it, and basically it makes a waste of money, the resources. And another risk that it poses is that the finished part can also be deformed, sometimes even beyond the end user's acceptability limits. So here, the team of Industrial Technology Research Institute have used COMSOL, a specialized feature, which is activation feature, to 3D prototype the simulation of this whole manufacturing process. They have used the various physics to actually optimize the part orientation and the support structure of this component during the build. And they further they were able to point out these design challenges that they were facing about the residual thermal deformations through the simulation itself. And further, they built an app out of it, so which basically helped them in reducing the testing time by 75%. Even the cost of labor, machine and materials were reduced by about 83.3%, and even time to obtain the outcome of this whole additive manufacturing process has been reduced by 99%. Because right now, before even going to further 3D manufacturing, they were able to perform the same through the simulation, which ultimately helped them in saving the material, time, labors. And another quite an interesting story is coming from RACAM RPG, which is about the optimizing railway equipment designs. Here, there are two devices that they work upon is auto-tensioning device and the modular cantilever assembly. So people who might have seen these railway beams, so they must have seen these auto-tensioning devices, which basically keeps intact the wires that run through the whole rail, and then this modular cantilever assembly. So, so basically, while analyzing this whole cantilever model, the RACAM team, they were able to quickly realize that the modular cantilever that they were working upon was rather bulky, and the stresses were distributed unevenly over this whole cantilever. So they then performed the structural optimization of the design and carried out a multivariable optimization, their objective was the mass criteria. So basically, using the whole topology optimization, the system's mass was reduced by about 75% to what they were having initially. And to point that they were using here the dynamic structural loading to emulate the whole impact of the train, which is around moving at 250 kilometers per hour. And even using the observations from the simulation analysis, the whole entire auto-tensioning device assembly was completely redesigned to incorporate a foldable design with a 50% reduction in the assembly size. And they even were able to replace this whole metallic spring with a polymer spring, where they used the COMSOL non-linear structure materials module. And all of these design changes basically led to 80% decrease in the weight of this design. Even the components were able to reduce from 12 to 5, and the weight of modular cantilever was reduced by 33%. And as I already mentioned, that the assembly size was able to 50% decrease. So this is how a couple of user stories that I wanted to take about showcasing how industry is using COMSOL in working upon their various kinds of objectives. Okay, so going forward, here is a case study from the thermal. The first study is from the thermal stresses, which is basically a very common problem in the automotive sector and aerospace and aviation industries. So this is an example where I've taken a temperature distribution over a disc brake. So as you can see in actual disc brake, this whole disc rotates and these pads are forced to push together. And now what happens is during the pushing of this brake pads over this rotating disc, due to the friction, temperature is generated, heat is getting generated, and because of that, there is certain kind of temperature distribution over the disc. This basically leads to the thermal expansion of both of these devices, and also the braking performance is also affected because due to this uneven temperature distribution and even the temperature rise above the limit, the friction lining gets fade away, which basically affects the braking performance. So to encounter those problems, before even going for the manufacturing, to evaluate what kind of design and how will it be playing role, how the convection will take the heat away, what will be the radiation heat transfer, what will be the conduction heat transfer, how the pushing of this brake pad will affect the temperature distribution. So for that, simulation has been done here to answer all of these queries. And another interesting example is from the heating circuit. So here at the top in the brake disc, we use the solid elements, but in this heating circuit, we have used the shell elements. So shell elements is basically used when we have got very high aspect ratio geometries. Like in case of this heating circuit, the circuit was very, very thin compared to the length what it possessed. So this basically poses a problem while during the meshing, and the meshing, the number of elements rises above very high level, which basically affects our computation time. The computation time is highly increased. So to encounter those things, we have got a shell interface here where you don't need to actually model it as a 3D solid body, but you model it as a surface. And the thickness part is analytically taken care and it is analytically meshed. So it basically helps in a reduction of the whole computation time, and the accuracy is certainly maintained. So in this example, what we had is a coupled electric interface, a thermal interface, and the structural interface. So we are solving for 3 different kind of physics problems. So here what we do is we have applied the potential difference across these both ports. And due to this potential difference, current flows through it, which basically generates the heat. And due to the generation of heat, this whole body is getting deformed due to the thermal stresses. Now here our concerns might be like due to the thermal deformation, whether this heating circuit will lose the contact or whether it may cause some kind of short circuit, which may ultimately lead in the burning of the circuit. So to answer all these questions, this simulation has been processed where a coupled structure, thermal and electrical analysis has been done. We can account for thermal expansion, thermoelastic damping, thermal contact, even Joule heating, and even you can account for the piezoelectric material, which basically responds upon that potential difference applied, or due to the stresses, it induces potential difference, and vice versa situation. Now here I've taken another interesting story from piezoacoustic interaction, wherein if you are interested in modeling the hydrophone, basically this hydrophone detects the submarines underwater. So in that case, you can couple a piezo device with that of a hydrophone, that is here the hydrophone, with any kind of acoustic waves that are being generated due to the movement of these submarines. So this basically can be achieved with the piezoacoustic interaction, wherein you can account for piezoelectricity, dielectricity, elastic modeling domains. So here what's happening is due to the movement of the submarines, it is generating some kind of elastic waves, and due to the acoustic structure interaction, this acoustic we are coupling these both together, and based upon the change in the acoustic waves, we are getting the structural response. And this structural response is basically using the piezoelastic material is coupled to electric currents interface, wherein we are detecting the change in voltage. So you see how the acoustic waves through the submarine is ultimately getting converted to the change in potential voltage. So through this, we can measure the submarine's acoustic waves. How far is the submarine? What is the speed of those submarines? So this is a coupled static, transient, frequency response, and eigenfrequency analysis can be taken care here. You can since here the piezoacoustic interactions have already been accounted for. Another quite an interesting story case study is coming from the fluid structure interaction, wherein the first part that we see here is the process of filling a water balloon, which is quite a vivid example for the interaction of fluid pressure with nonlinear structure material. In COMSOL, you can model laminar turbulent flows. You can model for single or two-phase, multi-phase flows. You can couple solid mechanics, multibody dynamics, shell membrane elements, any element with the fluid domain. So the one in COMSOL terms, we say things like two-way coupling and the one-way coupled model. I will explain you the difference. So let's say the example that we see here is from the filling of water balloon. And you see that as the fluid enters the water balloon, it expands the water balloon, which is made of membrane elements. Now, if we are only interested in understanding like how the fluid inflow is affecting the structural stresses of this membrane, so that will come into the one-way FSI, where we are not concerned about the other aspect, like how the structural deformation of this balloon is affecting the fluid flow inside. While in a vice versa condition, if we are only interested in knowing how the structural deformation is affecting the fluid flow, that will come in the one-way FSI. Certainly another example of this Rushton impeller, where we are churning the fluid and we can see how it is disturbing the flow inside, and even how the resisting force through the fluid is affecting the power that transmitted through the impeller, or how it is causing the structural deformations of this impeller. So here in this case, let's say for an example, if you're only interested in knowing how the rotation of this impeller is affecting the fluid disturbance inside, or that will come into the one-way FSI. But if you're also interested in studying how due to the rotation of this impeller, fluid is getting disturbed, and due to the resisting force of the fluid, it is, if you are also interested to know how it is deforming the blades of this impeller, that will come into the two-way FSI. So in COMSOL, we follow augmented Lagrangian Eulerian approach to couple fluid with any other structural phenomena. And as I was mentioning, you can model multi-phase flows, like in this example, how the fluid and air domain is affecting the deformation of this solid beam, which is hanging from the top. Another example of a one-way FSI, where this is the solar panel, and due to the wind flowing, if we are only interested in knowing what is the deformation caused in the solar panel, that will come into the one-way FSI. But if we are also interested to know, if this wind is deforming the solar panel, and this deformation of this solar panel, let's say, is affecting the fluid flow, that will come into the two-way FSI. Another quite interesting example is coming from the acoustic structure interaction, wherein the first example, I have modeled here a loudspeaker, which is basically modeled with a membrane. And you can see it is to be vibrating due to the production of sound. So here, I have not given any external stress or any kind of body input to this loudspeaker, but I have just generated the acoustic waves inside this loudspeaker, and we can see how the deformation is happening from the acoustic waves to the structure of this speaker. Just to let you know that this deformation is basically scaled up for better visualization. So basically, the production of sound is producing the stresses in the loudspeaker, and these stresses can be modeled using the acoustic structure interaction. And in another example, I have got a transient multibody analysis, which is performed to compute the gearbox vibration for the specified engine speed and external load. So basically here, the normal acceleration of the gearbox housing is firstly converted to the frequency domain. And this frequency normal acceleration is used as the source of noise. And then an acoustic analysis is performed to compute the sound pressure levels around this gearbox. So here we are interested to know how, due to the meshing of these gears, what is the kind of noise is produced around this gearbox. And another quite interesting feature from COMSOL is, hello. Okay. So another interesting feature from COMSOL is that you can actually convert this noise into an MP3 file, and you will be able to actually hear it, the kind of noise that is getting produced due to the churning. Then we have got various other application areas. The first one is the random vibration study of motherboard, where you can do a kind of study. Where we can answer questions like whether your model could fail, or how it will be able to sustain the objective. So basically, in this random vibration study, we enter the PSD data in the form of acceleration to any structure, and we can even account for the cross-coupling effects between various kinds of loading, which is basically given in the form of PSD data. Then we have got another interesting example of contact, which here where we have modeled the interference fit. So what's happening here is that due to the interference fit, some kind of structural stresses have been formed, and due to the contact, there is kind of opposing force or the resistive force that has been getting generated. So in COMSOL, you can either 3D model these interference fit, or even to ease out the process, COMSOL in the contact formulation itself in COMSOL, we have got an offset feature where you don't need to actually model the interference fit in the geometric body, but you can account them as an offset in the contact formulation. So those things will automatically be taken care of, and we can see the stresses generated, the friction that has been offered due to this interference fit. Then we have got another example from the Reciprocating Engine, where due to the rotation of crankshaft, we were interested to know the fatigue life of this connecting rod. And to make the process easier and computationally faster, since our critical region or the region of interest was just this connecting rod, so we have only modeled this connecting rod as a flexible element, while the rest of elements have been modeled as rigid. So it saves a lot of time in solving. Then we have got another interesting example from a biomedical stent, which have been used in vascular systems. So here, this biomedical stent is made of a shape memory alloy, where due to the temperature difference, like when it is put into the vascular system, it is just the cylindrical rod, but to the temperature of our blood and our arteries, it basically gets to the original shape that we have modeled with at that temperature. So which you can account for those nonlinear materials in COMSOL, as in the next example, where we have deformation in blood vessel due to the blood flow. So here we are solving for the complete analysis of two distinct but coupled procedures. One is the fluid dynamics with the calculation of velocity and pressure fields. Then we have got mechanical analysis with the deformation of tissue and artery. And actually here the tissues have been modeled with hyperelastic materials. So you can see how we can also account for various kinds of nonlinear materials. Then we have got another stability and stability analysis of a turbocharger. Here we have used the rotor dynamics module from the COMSOL. So basically here, if people who might be aware from the turbocharger, here we have got turbo hydrodynamic bearings to support our turbochargers. And what happens is like this so these bearings naturally have the cross-coupled forces present in them. And basically these cross-coupled forces act as a negative damping throughout the whole system. So here our motive was to know whether our turbocharger will be stable with these hydrodynamic bearings or not. So for that, we have simulated our turbocharger with the bearings, and we were evaluating the logarithmic decrement with the rotational speed of the rotor. which basically gives the idea of the stability state of the overall system. So here we see the top plot, which is average velocity, angular velocity versus the logarithmic decrement. And you can see that all the values with any angular velocity segment is always positive. So which makes sense that the logarithmic decrement will always be positive, right? So this tells us that without cross coupling forces, our turbocharger will be stable within this velocity range. Well, when we accounted for the same velocity range with the cross coupling forces due to the bearings, we can see that here the logarithmic decrement is getting some negative values, which depicts that these hydrodynamic bearings will be unstable at these certainly the angular velocity. So this gives us as an idea like how the stability and instability we working with these cross coupling forces due to the bearings on the whole turbocharger. Now this brings me here to discuss about some structural modeling capabilities. And the first one here I've taken is the structural non-linearities. So the first thing that any structural engineer would ever think of from the structural point of view is the non-linearities. So in COMSOL, you can account for any of the non-linearity, whether it is a geometric non-linearity or the contact non-linearity or the material non-linearities. In the geometric non-linearities, you can account for finite rotations, large displacements, stiffening, deformation dependent loads. So you can actually model the loads which are depending on the kind of deformation that has been caused. Then we have got structure contact non-linearities, where you can also extend this functionality to account for the friction, for the adhesion or the bonding between two surfaces. You can also model transient contact or the dynamic contact, I must say. So for dynamic contact, we have got specialized formulations which also account for the spurious energy release that gets lost during the dynamic contacts. Then you can also model wear. We'll talk about this structural contact in a little bit more comprehensive way in just next slide. Then we have got material non-linearity, where you can account for elastoplastic analysis. As you can see in this example of the diforming, where we are accounting for, we can see that here during the whole diforming process, there is also a geometric non-linearity while this die is pressing our body. So basically here we are also accounting for the contact non-linearities. And obviously we are going from the elastic region to the plastic region. So we are also accounting for the material non-linearities. So you can also model any nonlinear elastic material if you have any. COMSOL has got various models predefined with these all nonlinearities in built-in functionality itself. But if you have any other model which is to be specific to your own application, you can easily write those equations in COMSOL. So COMSOL gives us that flexibility to model those user-defined equations itself. So you can account for hyperelasticity, viscoplasticity. You can model for temperature-dependent models. You can account for creep. You can model damage and cracking phenomena. So as I was mentioning about the contact analysis, you can either model static or dynamic contacts. You can account for friction. There are various friction models present. You can even write your own friction model. So as of now, COMSOL allows two methods for the contact formulation, that is penalty and augmented Lagrangian. And for the dynamic context, we have got penalty viscous and augmented Lagrangian viscous models. So here we also have this adhesion and decohesion model where you can model the cohesive zone. So what happens is, like in this case of an example here, this both center portion was actually bonded together with an adhesive. So here and this end of the part is basically getting pulled apart. So we are trying to see how the debonding will take place through bodies which are being bonded together, and how will be the debonding, how will it be propagating throughout the structural contact. And similarly, in the bottom example, we can see the wear. So in COMSOL actually allows you to see how the material will be getting removed with any two bodies which are relatively in contact. So you can see here how the contact surface is getting changed, how the material is getting removed on this body, which is getting worn out. And also you can account for any initial stress and strain tensors, which if you have any residual stresses, you can account for external stresses, you can account for thermal expansion. And if you also want to account for the hygroscopic swelling, which is basically the effect of moisture present in our atmosphere, or if in any atmospheric conditions that you put your material into, if you want to analyze like what is the effect of the moisture present in the environment to your body, you can account for those things. Then we have fatigue module, which is basically the post-processing tool, which utilizes strengths and strain results from the structural mechanics to calculate the fatigue life. This fatigue life where you can use various stress-based models for high cycle fatigue, while for low cycle fatigue, we have got various strain and energy-based models. If you have variable load amplitudes, if the loads are changing with respect to time, you can model cumulative damage. While for the vibrating bodies, we have got harmonic vibration and random vibration facility to model the fatigue life with respect to the kind of loading that we are working with. Then, as I was mentioning, the composite materials module, so which is basically a very specific, very specialized tool for modeling composites. So as you see here, we have got an example of a wind turbine blade, which is modeled with around 100 plus layers. And this 100 plus layers, if you see here, the certainly top portion is comprises of various a number of layers, more than 25 to 26, which are very thin. While certainly the middle layers are certainly more thicker than the end layers. So to model this whole stacking sequence where the orientation of each layer may be different, or where the thickness of each layer may be different, or even where if you want to do some kind of experiment, like changing the kind of stacking, changing the kind of orientation. So for that, COMSOL makes it very easy to model these laminate together. And as I was mentioning, that you don't need to model this as a 3D solid body. You just need to model it as a surface body, and you with specialized tool, you just have to provide the material like laminate property, like whether how many layers does it consist of, how many number of orientations does it have, what kind of orientation does it have, what is the thickness. And COMSOL will automatically take care of the whole stacking thing over this whole wind turbine blade. And with our specialized post-processing tool for modeling to understand like where every interlaminar stresses to actually in the post-processing, if you want to visualize the stacking, the orientation of each layer, the stresses that have been produced in each layer, so you can evaluate those things very easily. So for modeling composite layers, analyzing composite layers, we have got two specialized theories that it work upon is for the layer-wise theory and equivalent single layer theory, which is basically kind of used in any of the application. So then you can also account for any kind of non-linear material property. You can account for plasticity, hyperelasticity, viscoplasticity with this composite materials module together. You can even couple it with any of the physics, whether be it heat transfer, electromagnetics, acoustics, or even fluid flow. So as I was mentioning about the interlaminar stresses, so you can even visualize the interlaminar stresses, like in this case of this body where it comprised of around 6 layers. So here we can see the stresses and deformation in each of the layer, and we can actually see the deformation of whole body, which is combined of a stacking sequence together. And actually you can model the delamination of these layers. So since a composite is formed, a laminate is formed of various composite layers. So in a kind of loading, this laminate may even break the bonding between any of the two layers. So you can also model these first ply failure criteria with the delamination. You can see which lamination which where at exactly which layer will break at which point. So there's here we have got another rotordynamics module, which where you can take account of various kinds of stationary and moving rotor components, including discs, bearings, and foundations. So here you don't need to actually model those bearings and discs. COMSOL has a predefined functionality with where you can just specify what kind of bearing do you have, what is the kind of clearance, the various other structural properties. So you just mention them and COMSOL will take care of those things automatically. These are some of the bearings that are predefined, that are journal bearings, thrust bearings, rolling element bearings. The result presentation, these are by default. And anyways, you can plot anything that you may want to evaluate. Then we have got Multibody Dynamics module, which is for the assembly of various components. We have got predefined various joints together. You can even, like in this case of these gears and the chain sprockets, so you don't need to actually model them. COMSOL have them predefined in the library. So you just need to provide the properties of this, like what is the addendum and dedendum, what is the pitch circle diameter, similarly other things, and COMSOL will take care of all those things automatically. Yeah, so these are some of the joints. The functionality, you can account for friction, you can account for thermal expansion of at any of the joints, you can apply force, movement, torque, you can even apply any kind of locking mechanism in the joints. And these are some of the joints that are predefined in the library. So nonlinear structure modules, I guess we have already been through it. Okay, so going forward, let us have a look at a coupled solid and thermal phenomena. I will take you through an example model where we will see how to set up an example of modeling structure and heat transfer physics together. Let me just open an instance. So yeah, so I hope most of you are well aware with this GUI, since Dr. Antis has taken you through it. So Model Wizard basically assists you in setting up your problem, whether it is 3D, 2D, 1D. Then you can also account for what kind of physics that you want to solve for, whether it is a solid mechanics physics or whether it is, let us solve for heat transfer in solids also together. So we can add multiple physics here. And then we can specify what kind of study that we want to perform. Let's say here I want to perform a stationary study. So let me just apply this. Okay, so this is the GUI of COMSOL. And the first thing that one want to do when we start the simulation is either building our own geometry. So you can go to the geometry, you can use various utilities that we provide for building geometry, or you can import your geometry. Let's say if I go to browse, okay, let me just. Okay, I will import a geometry. And let us see. Yeah, so this is the geometry of the file, and the next thing that we want to do is defining our material. So let's say if I go and you can search any material here. Let's steel, and even you can define your own material. So if you have anything specific, if you want to specify your own material, so you can just right click here and you can add a blank material. So based upon, as I have already included this in the solid mechanics and heat transfer physics here. So based upon, as I will select this domain, if you see, it will automatically show us what properties are actually required to solve our simulation. So the one way can be either you can add your material and then add the physics, or the another way can be you can first add your physics and then define the material. So by this way, you will be knowing actually what properties are required to solve the physics that we have called. Let's say for solid mechanics, we will be needing Young's modulus, Poisson's ratio, density. Similarly, for solving heat transfer, we'll be needing density, thermal conductivity, and heat capacity at constant pressure. We'll just delete it, and we can specify those values here. We can even define it as a function of temperature, function of spatial coordinates. Let's say in the case of functionally graded materials, so we can just edit these things here. We can define through some kind of analytic function or through some kind of interpolation function. Let's say for solid mechanics point of view, let us first start. The good approach is first, let us first start applying a boundary conditions or the constraints. So first thing, let's start applying the constraints. So let's say I apply ruler condition at the bottom of these plates. So here, what it will mean is it won't be allowing any normal deformation of these surfaces, but it will allow in plane deformation of these bodies. Similarly, let us apply spring foundation. So here we'll be analytically applying some kind of stiffness to these surfaces. Let us apply. I can specify the spring type. Let's say I apply this in the diagonal. I just want to apply it in XY plane, X in Y direction, not in the normal direction, since we have already constrained it in the Z direction. Now let us apply convective heat transfer from this body. Let's say I will select all boundaries except this both. And then we can specify whether it is what kind of flux type. So let's say here apply a convective heat flux with the heat transfer coefficient to be tan and the atmospheric temperature, external temperature to be 293. And then let us apply another heat flux at the bottom of these plates. So we can apply some inward heat flux. Here we apply it as 1E4 watt per meter square, and then we can couple together. So if we don't use this multiphysics coupling on this domain, what system will do is it will solve for both of these physics independently, and we won't be seeing the effect of one over each other. But when we apply the thermal expansion node, so by this you can couple both the physics together, and we can see the effect of one over the other. Let's see. Let us hit solve. And this is the progress step where you can keep track of your elements of the progress of your simulation. And this is the convergence plot window. So you can, this is mostly helpful when we are working with the high non-linearities to track our problem, how our problem is working through, whether our problem is getting converged or not. You can also check through the logs how our problem is progressing with various iterations with various input parameters. Let's say if it is a sweep of some parameter or the time. So here we can see these are the default plots generated, and we can see some deformation that has been produced in this body. Now, if you remember, we have not given any kind of boundary load to a bracket, and we have just applied some constraints over this body. But in the heat transfer, we are given some heat flux, convective heat flux, and an inward heat flux. So this means that the solid mechanics heat transfer phenomena is being coupled together, because the only source of structural deformation here is the thermally induced deformation. So, okay, then we can check how the temperature is getting changed throughout this body. We can see here at the bottom, we have around 428 Kelvin, while at the end of these brackets, we have got the temperature is getting reduced to 310. So this is basically the steady state of our system with convective heat flux and the inward heat flux. You can also visualize the isothermal contours. Okay, so do we have any queries here? Because I think I'm well done with the presentation that I came with. And now we can have Q&A session. If you have any queries, please feel free to type in the chat box, or even you can unmute your mic. Hello.
Yes, sir.
Yes, sir. So do we have any queries? Please feel free to ask. We can take up as I'm towards the end of my presentation, we can discuss any Q&As.
Right. So first of all, thank you, sir, for the wonderful presentation showing the capabilities of COMSOL software. So from my personal experience, I have been using COMSOL from last 3 years, but today I feel that I know only 10% of COMSOL. So thank you for that opening my eyes. So I request all the participants to ask the questions and take the advantage of this platform.
Good afternoon, sir.
Good afternoon, sir.
Sir, actually, you had shown in your presentation that I section where you had showed the temperature and the stress part. So can we have that model in our application library?
Which example? Let me just get.
There was layer-wise I section.
Okay. That was from the composites, right?
Maybe, sir. That.
Yeah,
that one, sir. Is it available in our application library of COMSOL?
Yes, this is also available in the application library of COMSOL. Let us check. Yes. Composite. Basically, here instead of directly applying the heating condition, we are using the power beam source as a beam as the heat source. So basically, a beam is getting impinged over this body, and it is basically we are trying to move it from the bottom to the top, and we are trying to see that during the whole movement of the heat source of the beam, how it is causing the structural deformation of this I section, which is consequently made of composite laminate.
So for that one, sir, in this module, it is showing that the beam is moving towards Z direction. We can also move from X or Y direction also.
Yeah, we can.
We can check the results of that one.
Yes, we can do that also. I will check if it's downloading faster. I can even show you. So basically, we can any of the boundary condition, not just this beam heat source. We can apply any boundary condition which is varying with respect to the spatial coordinates or the temperature. Yes. So we can model, let's say, for an example, a moving body load. Let's say for this example itself, a body load is moving towards any direction. So you can make it either as a function of interpolation function, or you can directly give the coordinate system. So that will be like some kind of playing with mathematics. So we'll be defining a function which is x and y or any coordinate dependent. Let's see here if I see. Okay, so this is the origin point of beam. So I guess there must be some kind of function defined. Okay, so this yp is the function most well. It is a function of y, right? Yes.
Yes, sir. It is moving in y direction.
The y direction. So here we have defined it as the function of y. Similarly, if we wanted to have it as a function of x, so we could have defined it as x. Y, we can define it as x square plus.
Okay, so for the moving heat source, we have to define in that bit beam origin point, or we can define in the definition also.
We can define. We can use here instead some piecewise function or any kind of analytic function here, which may be a function of let's say any time. We might be varying it with respect to time. So we can define that function here, either analytic or piecewise. So similar to that expression that it had earlier based upon the YP.
Yes.
Have it as a function here and a parameter, let's say it is also time. So with time, this YP will be changing. And similarly, we can directly use this function here, that is an1 of t. So I think we have got a blog also here. Okay. Yes, you can even refer to this blog here, where it is shown like how to model conditional boundary conditions. You can even either the loading may be varying with respect to the coordinates or even with respect to time. Like in this example, is
Yes, sir. Moving heat sources there. That.
I will copy this link in the chat window. Maybe you
Yes,
can
sir,
have
that will be very helpful to us.
both of this example also. I will try to make it here. Okay, so I have pasted it in the chat window.
Okay, thank you, sir. Sir, can I ask one more question, because I think it is a bit related to my work also.
Yeah, sure.
That material properties that we are adding.
Mm-hmm.
So I am giving on that in piecewise. Like there is some option in my material. It is piecewise. It is temperature dependent properties.
Okay.
So at the time of simulation, it will call automatically, or we have to define in somewhere. The material subpart, there is a piecewise function.
Yes. So okay, I will
suppose if you take any material, it will be very easy.
Or else I can open an example here right now.
Because I am not sure that it will call or not.
Yeah, actually what will happen is it will call, let's say here, okay, these are the constant properties. I will just take an example. We shall be having something in this. Okay, yeah. Temperature dependent plasticity, right? Of material property, which is basically dependent on the temperature, right?
Yes, sir.
Okay, so what happens is if we have defined any material property which is a function of temperature, and if we are also solving for temperature here, let's say in this example we are solving for both solid mechanics and the heat transfer. So it will basically be updating temperature value at every instant as depending on the boundary conditions. And here in the steel, yeah, so these are all the functions of temperature. So as this temperature variable, we are basically not using any constant function here. Here, these all functions are defined as a function of another variable. This FA is some kind of interpolation function. Here, our input variable is the T, but when we have called this function FA, we have defined it as a function of capital T, which is a predefined variable of COMSOL for the temperature.
Oh, okay.
So as we will be solving for heat transfer equations, this temperature value will automatically be getting updated. And based upon that, this alpha coefficient of thermal expansion will also be getting changed in the manner similar here. Like from 50 to 100 Kelvin, it will be somewhat in this range. Similarly,
it means it will directly call that equation.
Yeah. So
okay, thank you, sir. I was confused that it will call or not, because I am getting some plots like this.
So like if in your case, if you need any other variable which is not temperature, right? If it is some other variable, let's say some constant C, so you can define that variable in the definition as a variable. And this variable will also be getting updated as simulation progresses. So this value of the variable, well, name C, will be getting updated with respect to time of any other entity, and it will again be updated in the whole scenario. But if we are making it as a function of some kind of parameter, let's say here a parameter was this, which will basically be constant with respect to simulation. So it will be constant throughout.
Oh, yes, sir.
For any
I will
changing
get here.
quantity, yeah, we shall define it in the variables.
Yes, sir. Thank you, sir. Now my doubts is totally solved for you.
Yeah, thanks. Glad to know that, sir. Okay, so does anybody have any queries? Okay, we can wait for a minute. If you encounter any query, you can please feel free to ask. By the time you can search any blog post at COMSOL at /blogs or videos. You can even go for the user stories for the people who have already used COMSOL in their in the commercial industry. Similarly, for academics, we have got paper publications here. At the COMSOL website, you will find these publications. You can, if for anybody else, it can be useful in their simulation. It can give a good idea how that thing can be implemented. Similarly, goes for the user stories. You can check any of the user story for the companies or the people that have worked with. Similarly, you can go with, as a Dr. Antis might have shown you, the application gallery where you can find various example models. You can search anything relatable, let's say composite, search anything related to composite. You get this relevant examples. You can filter by product or the discipline. And if you have any queries, you can always connect with us at our support portal. So if you have any queries with your projects or anything, if you want to work with, so you can ask at as comsol.com/support, or if you have any other queries related to our tool for the purchase or any other thing, you can contact as comsol.com/contact. Okay, so I think we can hello.
Yes, sir.
Yes, so I think we can conclude.
Okay. Okay. Before concluding, is there anybody who is having doubt? If not, we can close today's first session. Jain sir is the speaker for the next session only. And for this session from our 10:30 to 1, we have finished. So I declare that we'll regain or we'll join again at 3 o'clock. Am I right, sir?
Yes. At 3 o'clock?
Yeah, okay. So, yes, sir.
Yes, sir. 3 to 5, we have got another session where Dr. Antis will take an hands-on, so you can perform any simulation. I think he will be taking some examples together with everyone, so you can parallelly work with
the
model. And if you want to explore any functionality, any query.
Yeah, sure, sir, sure. And hope that everybody might have downloaded that COMSOL software on their PC, and we can have live demo on that. And they can simultaneously open that COMSOL software on their PC, and they can do the similar things as we are learning it. I'm very much thankful to Jain sir for giving such a nice presentation, and also I'm thankful to everybody who has joined this EPDP. So thank you one and all. We'll join at 3 o'clock. Thank you.
Yeah. Thanks everyone. Have a very good day.
You too. Thank you.